This is section 11.1. We're looking at two quantitative variables, and we're going to use scatterplots and correlation to do that. So let's start with scatterplots. A scatterplot shows our relationship when we have two quantitative variables, so two numerical variables. So for our first example, we have a scatterplot of the heights of father-son pairs. So this goes back to your math classes when we had graphing with coordinate pairs. So like this dot right here, that represents a father that is 72 inches high that has a son of 76, that's 76 inches high. Now every dot represents one father-son pair. So this dot right here represents the father and son together, and this dot right here would be a different father and son that come together as a pair. And what we would probably want to do in statistics is we probably want to do something like use the father's heights to try and predict or get information about the son's heights. So in this case, if we want to do that, the explanatory variable would be the father's height, and the response variable would be the son's height. Our explanatory variable is always the one that we are trying to use to explain. The response variable is always what you want to predict. Okay, so let's make ourselves a note about that. So the explanatory is what you are using to explain something. The response is what you want to predict or explain. So we want to use the father's height to predict or explain the son's height. Now, this isn't always set in stone. A different researcher might come through and they might actually want to do the opposite. They might want to try and use the son's height to predict the father's height. And so then their variables would be switched. But it's just based on what you want to do in your study. When you decide what to put on which axis, the explanatory variable is always going to be on the x-axis. You can remember that because explanatory has an x in it. The response variable is plotted on the y-axis. Okay. And usually we're using that explanatory variable to predict the response variable. Okay. When we want to analyze scatterplots, we have to look at several different aspects. We're going to look at the direction, the form, the strength, and we're also going to look to see if there's any unusual observations, which are sometimes called outliers, depending on how unusual they are. So first, strength. We have a strong association when you have plots that look like this. Notice if I was to draw maybe a football around these, it's going to look like a pretty skinny football. Or if you were to draw a line through, the points are pretty close to the line. Okay, so if I was to erase this football and draw a line, you can see that the points are pretty close to the line. Okay, or if you have a football, it's a pretty skinny football. This means that knowing one variable is going to help me a lot in predicting the other variable. So if I was to look at, say, if this is my x value right here, then there's not a very big spread in the y values that go with that specific x value. I could probably make a pretty good prediction. For weak association, when there's a weak linear association, the points are scattered loosely about the line. So knowing about one variable doesn't help much in predicting the other variable. So if I was to try draw a line through here, the points are not very close to the line. And if I was to try and draw a football around it, it's a pretty fat football. So strong association, you'd have a skinny football. Weak association, you'd have a very big football to fit around it. Or over here, you can see the line, you can see the points are not close to the line at all. We'd have, again, a pretty fat football. Okay. And if I wanted to predict the y value for these x values, there's a lot of different x values. I can't really tell you how accurate well, I could tell you, I can measure that mathematically, but my predictions are not going to be very close, okay, because the y values have so much scatter for that one x value. Okay. And no association just means that the two variables don't seem to be related at all. They seem like they're just randomly scattered. In fact, how would you even do a line? Would your line look like this or this or this or this? Like you can't even figure out where the line would go. They just seem like they're randomly scattered. Then we look at direction. You can either have a positive direction or a negative direction. So a positive, we're going to call it an association. It's like a relationship. It means that as the values of one variable increase, so do the values of the other. So, or if x goes up, then y seems to also go up. X goes up, y goes up. Doesn't matter how strong it is, it's just the direction of the line. We seem to be going up. So x is going up, y is going up. Negative association means as the values of one variable increase, the values of the other variable decrease. So as x goes up, y is actually going down. X goes up, y goes down. Or if you were to draw a line in there, your line would have a negative slope. Sometimes that's an easier way for me to remember it since I have that math background. Then we look at the form, which is what shape. So it's basically what shape. You have two options for this class. You can say that it's either a linear pattern, which means a line would be a good fit for the data, or a nonlinear pattern, which means not a line, or in other words, a curve would be a better fit for the data. So here's a bunch of different examples of where a line would be a good fit. So you can see the line, or if we can put a line through these, there's the lines already in that one. You can put a line through. These would all be very linear. Okay. Then you have nonlinear patterns where a line is not a good fit. So really a curve would be a better fit here. The computer will try and put a line through if you ask it to, but that doesn't mean it fits the data. Or here we'd actually need a very intricate curve. Okay, lots of curves there. This one, we'd need some kind of curve like this. This is a slightly more subtle, but still going to be a curve. This one, some people might think that you could put a line through right there, and maybe you could, but I think it would actually be better fit with a curve right there. So this one is a little bit more subtle. Okay, but I still feel like a curve would be a better shape for that data. Then you have unusual observations. So we want to look for observations that seem to not fit with the rest of the data or to be far away from the rest of the data. Now, deciding if the observations are far enough away to be officially called outliers is a graduate level topic. I sometimes teach this in a 5,000 level course. We actually spend a lot of time on it, and it is a very involved topic. For us, we're just going to say of whether or not we think it looks unusual. So looking at these different examples, okay, here's a bunch of my points. Do you notice these 2 points up here? I would say that these are definitely going to be unusual. Okay, probably even going to be outliers, but we're not going to really teach you how to tell for sure. Looking at this one, I feel like maybe they're fine. I mean, maybe these ones are maybe unusual. They don't look as bad as the ones up here, so maybe they're unusual. We'd really have to know more to be able to tell for sure. Again, this one, I'd say it's probably unusual. Actually, looking at it again, I would probably say, yeah, it's going to be unusual. Because look at how all the rest of these points are down here, and that one's way up there. Okay, but what about this one? This one is definitely unusual. So again, anything that's unusual just counts as any point that doesn't seem to fit with the rest or seems to be far away. So a lot of these were ones that just didn't seem to really fit with the rest of the data. But even if I put one like out here that seems to fit with the rest of the pattern but it's far away, that would still count as an unusual observation. So now let's talk about correlation. Because what happened is we looked at lots of scatter plots, and some people say this is a strong relationship and some would say it's weak, and sometimes they might argue a little bit. So we said, let's come up with a less arbitrary, a more defined mathematical way to measure the strength of our relationship. So we came up with the correlation coefficient, and it measures the strength of linear association between two variables. It doesn't work if you don't have a line. Okay. So our correlation goes from -1 to +1. It's going to be -1 if your points are exactly on a line. It's going to be +1 if your points are exactly on a line, but negative just means your line is going down. Positive means your line is going up. Okay. You can see this is a correlation -0.7, +0.7, so line going down, line going up. The points aren't exactly on a line, they're kind of in the middle. But r equals 0, the points are just kind of exactly randomly scattered. There's no relationship. You couldn't figure out where to draw the line. Okay. And so every scatter plot can be somewhere between -1, 0, and +1. Just depending on how close they are to the line. You'll notice that r will always be positive if the scatter plot has a positive association, or if you want to think about it as a line, if the line has a positive slope, which we will learn how to do lines later. But if you want to just draw on the line by I, r will be negative, or the correlation will be negative if you have a negative association, so the line has a negative slope. And correlation then, it just measures how close the points are to a line. So let's look at some more examples. So here are more scatter plots with their correlations, and we're going to guess the missing correlations. So when I look at this first one, notice how if I was to draw a football on a perfect circle, I can't figure out where does the line go. Does it go like here, here, here? Because the points just seem to be completely scattered. Okay. And so I'm going to guess this one be a correlation of 0. This one has a written in for us. This is a correlation of 0.4. So our football's still pretty fat. We're pretty randomly scattered. Okay. If I need to figure out this one, but notice this one says 0.8. So I know that this one has to be between 0.4 and 0.8. So I'm going to guess, and I can tell you because I have it written down, that my correlation is 0.6. Okay. So here's one that has 0.8. Here's one that has 0.95. So at 0.8, our football's getting fairly skinny, but our points still aren't just on the line. Okay, here's at 0.95. We're getting really close to the line. This correlation happens to be 0.9. Okay. Now let's try some negative ones. So this is a negative 0.3. So our points are pretty loosely scattered here. Okay. And then we have several different ones until we get all the way up to this one says it's negative 0.95. So this one is a correlation of negative 0.5. This one is a correlation of negative 0.7, and this one is a correlation of negative 0.9. So see how our points keep getting closer and closer to that line. This is a correlation of negative 0.95, and this one is a correlation of negative 0.99. Let's try this example. We want to match each plot to its correlation. So here's our possible correlations, and we need to figure out which one goes to which. I like to start with the strongest or highest numbers and work my way backwards. So like 0.91 is the biggest number there. It's positive, so I need one going with the line going up. This seems to be the strongest. So this one seems to be a very strong correlation, and it's positive, so I'm guessing that one is 0.91. Now let's see, what else do we have? This negative 0.79, that's a pretty high number, pretty close to negative 1, and it's negative. So I would guess it's this one right here. It seems to be fairly strong, so negative 0.79. Let's see, we have a positive one here. This one, I'm having a hard time telling for sure if it's positive or negative. And this one seems to be going down. So I would say this is negative 0.43, probably goes here, because it seems to be maybe not fairly strong, but it's moderately strong, going down. 0.59, that must be this one, it's moderately going up. And the one that I couldn't really tell if it was going up or down must be this one for negative 0.11. It's pretty close to 0. So here's two different websites that you can go to practice guessing the correlations. The objective for this, it says you do need to be able to guess within 0.3. That means I don't expect you to know if this one right here is 0.4 or 0.5 or 0.6, but you should be able to guess that it's somewhere between 0.4 and 0.6. Like you should be able to tell it's not all the way up to 0.9 and it's not all the way down to like 0.1. Okay, it's kind of moderate, gets somewhere in the middle, like around 0.5, give or take, about like 0.3. Now, again, just as another caution, correlation only works when we have a linear relationship. So by definition, it mathematically measures the strength of a linear relationship. You cannot apply it to nonlinear data sets. So you should always look at your data to make sure it actually is linear, because computers are great at following orders. They will compute correlation for any data set that has two quantitative variables, but it won't mean anything. Okay. So I asked the computer to calculate correlation for this data set. It dutifully reported that my correlation is 0.27, but that doesn't mean anything because the data is not linear, so I can't use correlation for it. Okay. And if someone ever says, oh, my correlation is 0, that doesn't necessarily mean there's no relationship. It just means there's no linear relationship, because again, correlation's only for linear data. And another caution, that correlation does not imply causation. So just because X and Y are correlated, it does not mean that we can say X causes changes in Y. So for example, in children, shoe size and reading ability have a strong positive correlation. So here's some sample data. You can say it's pretty strong. But does higher shoe sizes cause higher reading abilities? Well, obviously not. No one's going to agree with that. Okay, this one had a confounding variable of age. Okay, because as you get older, your shoe size increases, and as you get older, your reading ability also tends to increase. Okay, and so this isn't a cause and effect. This is just they're related. It also does mean, though, I could probably use shoe size to make pretty good predictions about the reading ability, but it doesn't mean that shoe size causes reading ability to change. So now for our big example for today. It's on Facebook friends. So it starts with, how many Facebook friends do you have? Does everyone have the same amount? Like, what might explain some of the variation in Facebook and the number of friends? So this was a very big study. We're going to look at just a small part of it. Okay, and so these researchers examined the relationship between the number, and it was just self-reported, of Facebook friends and gray matter density in different regions of the brain. Some of these regions have been linked to social perception and associative memory. And the researchers performed MRI scans on students at the University College in London. And their research conjectures, they want to say, does Facebook use swell the size of brain regions devoted to tracking and maintaining relationships? Let's go through our 6-step process, or as many steps as we know how to do today. So step 1 is ask a research question. So they specifically want to know, if we narrow down, does having more Facebook friends swell or increase the size of brain regions devoted to tracking and maintaining relationships? Step 2 would be to design a study and collect data. So there's the article. And what they did, they designed it, they said, we'll perform MRI scans on students at the college. The results for the left middle temporal gyrus, which has been linked in other studies to face recognition, was examined from 40 student volunteers. So let's go through and fill out some important information. So first is, what are the observational students? So the observational units would be the individual 40 students. The sample size would be 40, there are 40 students. The explanatory variable is the number of Facebook friends. That's what they're trying to use to explain something. And it is quantitative. You might wonder why we make you guys do this on every problem for the entire semester. It's because knowing what kind of variables you're working with will help you decide what procedure to use when you get to the final and everything is mixed up. The response variable is, let's see, if we go back up or down, I think it's measuring the size. So it is the size of the region. And it is also numerical. Or numerical. So numerical, so I meant to say quantitative. Now, is it an observational study or an experiment? Well, are the researchers controlling anything? I would say no, it didn't say they controlled how many Facebook friends they had. They just reported how many Facebook friends they had. So I believe that this is an observational study because the researchers just watched and collected data. Okay. They did not control how many friends the subjects had. Is it a random sample? I would guess not, because they mentioned the students were volunteers. And what direction did the researchers believe the relationship would be? Well, they thought more friends meant bigger brain, or maybe I think it's actually measuring density. So bigger brain density or higher brain density. So they think that if you have friends here and your density here, that it should probably be going up, right? More friends means more density, so they're guessing it's going to be a positive association. Always draw it out and then try and figure out how to answer the question. Just for review right here, when we ask observational study or experiment, that's going to be saying, can we do cause or effect? In this case, we're not controlling anything, so we can't say cause and effect. That's why we ask these questions, because we want to figure out, can we say cause and effect? And why do we ask if it's a random sample? Because if it's not a random sample, we can't generalize to the entire population. We can only say, well, maybe these results will carry over to people similar to the volunteers in our sample. Now let's explore the data. So for convenience, we have defined the number of Facebook friends in terms of hundreds of friends. So a result of 2.18 does mean that the student said 218 friends. And the brain density measurement is in some arbitrary units that we don't know. So we'll go to the ISI applets. And in there you have quantitative response. And you want to go this one that says core/regression for correlation/regression. And this data set is already built in. So we just come down to Facebook. Oops. Wait for it to change. Click use data. Don't forget that. And you want to check and make sure that you have the right explanatory and response variables. So they did put friends on the explanatory, they put density on the response, so that's good. If they had it wrong, you could click this button right here under the data and it will switch which variable is on which axis for you. So again, friends on the x-axis, density on the y-axis. Now let's describe this scatter plot in terms of direction. So if I was to draw my football around here, it does seem to be going up, so I would say the direction is positive. My strength, I'm not sure on this one. Okay, I don't seem to be super close to a line, okay, but I also don't seem to be super far away. So I guess maybe something moderate, not super strong, not super weak. I could guess anywhere from like 0.4 to 0.7. My form, it does seem to be linear. The line seems like it would fit it just fine. What about unusual observations? If I delete everything, this one's maybe a little bit farther away, but it does seem to fit with the rest of the data. So maybe, okay, so 1 fits the pattern, but a bit farther away. Doesn't look super bad, but maybe we can at least look at it. What about, is there an association between number of friends and density? If you were to look at this, do you think that there seems to be an association? I would say so, right? Like more friends seems to lead to more density. So I could say something like, I think so. More friends seems to be related to higher density. Do you think that knowing a person's number of Facebook friends would help you to accurately predict their brain density in this region? So if I pick someone that had 600 friends and I went up, do you think you could predict what their brain density would be? Well, maybe not exactly. Like maybe they're up here, maybe they're down here, but would you have more information, or would it be different than if you were guessing it like 2 friends? I would say like you can probably predict a little bit, not a super good prediction, but you can make a prediction. So I would say, yes, I think it would help you predict, but because the points aren't super close to a line, your prediction won't be super accurate. Okay. It's still better than nothing, but it's probably not going to be super accurate. So we guessed our correlation up above before it told me to. So I'm going to guess maybe R is like 0.4 to R equals 0.7. I just think it's kind of somewhere in the moderate level. But let's go to our applet and find the correlation exactly. So I click on this button right here, correlation coefficient. Ooh, I guessed optimistically on that one. It was actually R equals 0.366. So don't feel too bad. I've done this for years and years, and I still overestimated a bit on there. Now let's talk about outliers and correlation coefficients. So correlation is very sensitive to outliers. The more extreme the outlier, the larger effect it can have. What we do is we say the correlation is not resistant to outliers. It can't resist an outlier. So let's use the applet again with our Facebook friends to move a point and see what happens to the correlation. So in your applet, you can actually click on a point. It will show you the X value. It will show you the Y value. And then you can do various things. You could delete that point and see what happens. Or revert, I can put it back in. I can click on the point and I can actually move it around. Before I can move it though, I have to click on the show data options and I have to click on move observations. So you can actually add in observations, you can move observations. So watch right here, the correlation is 0.366. If I move it closer into this middle of the cloud, notice my correlation actually changed. What happens if I move it like way over here? Notice my correlation changed a lot, all the way down to 0.117. If I move it way over here, my correlation changes a lot. I can make it go almost all the way to 0. Or I could maybe put it, trying to put it so it fits with the data. If I put it like this, notice now my correlation jumped all the way up to 0.9. Because if I put it way out here, it thinks it's with the pattern and it makes it look like it'd be a really skinny football by the time you have all of those points and this one way out there. So I could make my correlation go from almost 0 to almost 1 just by moving 1 point. And that's really what we want you to remember, is that just 1 point can completely change your correlation. Okay. So I have a few written on here for you. So this was our point that we said maybe it was unusual. This is my original data set, the correlation 0.366. I first deleted it and my correlation actually went down a little bit. Okay. I moved it out here so it fit with the pattern. Okay, so it fits with the same pattern, but it's way out here far away, and my correlation jumped all the way up to 0.72. Or I moved it way down here. So here's my pattern, and I moved it way down here. So it doesn't fit with the pattern, and look, my correlation dropped all the way to 0.047, and it even changed to a negative. So it even changed signs, okay, because now it thinks we should be having a line going like this. Okay. But if this is your pattern and you move a dot far away from it, it's going to completely ruin your correlation. Okay. So if the unusual observation is far away, but it seems to fit with the rest of the pattern, so like this one right here fits with the pattern but far away, it makes the correlation stronger. But if our unusual observation is far away and does not fit with the data, like this one, it makes the correlation weaker. Okay, but really what you have to remember is that a single point can completely change your correlation. So here's just another example. This is my original data set for just a different data set. Okay, I have a pretty high correlation of 0.8649. I added 1 point up here. Okay, so here's my data. I added 1 point that did not fit with the data, and it dropped my correlation to 0.6504. And then this is the same data, okay, but I added another point so far out here that it changed the scale and made it look like it was changing. And I added a point so far away, my correlation dropped almost to 0. Now, sometimes our data would actually be better if we split it into subgroups before we analyze it. So one example I really like is we can look at the world record times in seconds for the 10,000 meter run for men and women. And we want to be able to predict the world record times based on the year. So we put the year here, we put the time in seconds for the world record on the y-axis. And this is all of our data for both men and women together. Notice my correlation is really small. And if you were to try and draw a football, how are you going to draw a football around that, right? Like, this one just looks really weird, okay? You can't really figure out where to draw the line. There's two distinct patterns, okay? You should not analyze data that looks like that. That's going to be bad data to do linear regression on. But we noticed someone checked the time to actually explore this data, and they're like, oh, there's men and women in the same data set. Like, what if we split them out? So they graphed men separately and women separately. And notice when we graph men separately, my correlation is almost 1. And when we graph women separately, again, my correlation is almost up there at 1. Both lines fit very well. We could make very good predictions, okay? But this happens quite often. Sometimes we look at one data set and really we should divide it into subgroups, okay, to actually analyze it better. And often when you divide it into subgroups, your correlation can change. Sometimes it'll change higher, sometimes it might be lower, but your correlation can change if you split it up into subgroups. So we're going to go back to our applet and use the applet again to look at the foot, height, hand data set. So we click Use Data. This data set, they were using height to try and predict hand span. So looking at this, I would say, okay, looks like we have a positive correlation. Looks like we're maybe moderately strong. Oh, we might have an unusual observation. So before we split it, let's write down all of this useful information for us. Like, what are the observational units? So it doesn't have a lot of information for us, but the observational units here would be each person. Okay, so each person has a height and a hand span. The explanatory variable is height, because we're trying to use that to explain or predict hand span. Our response variable is hand span, and that's what we want to predict or explain, and that is quantitative. It's numerical. And height is also quantitative or numerical. My strength, and if I was to draw in my football, It's not super weak. It's not super strong. I'd probably say my strength is maybe moderate. My direction is definitely positive. My form, could you draw a line through here? Yeah, I'd say you could probably draw a line through there. It looks pretty linear. What about unusual observations? I would say so. I would say yes. That one that's about 60 for the height and maybe 23 for the handspin. And let's guess our correlation. Again, kind of moderate. I'm going to guess like 0.5 or 0.6 maybe. But the interesting thing is this data set has males and females. And we know the males and females on average have different heights, and I would guess they probably have different handspans too. So in the applet, what we do is we come to our applet, and it says response variable, handspan, explanatory variable, height, good, color by, and I can click on gender. And notice now it will split it out. So males are blue, so they're up here. Females are red, they're kind of down here. And let's come back to our notes so we can write. It kind of seems like two distinct groups. Like this is the females and this is the males. They seem like two different groups. Okay, and the fact that they are so distinct tells me I should definitely take gender into account when analyzing height and handspan. I use a different program to actually separate the two data sets. You can't really do that in this applet because it's pretty basic. Sorry, I had to go into Excel. But if I look at just the females, so here's just the females, they have a pretty high correlation. The interesting thing is if I look at just the males, the correlation actually drops really low because the females aren't there to try and make it look like a whole line. Okay. The reason why is that one outlier. In fact, if I take out that outlier and I look at just the males, then I'm all the way up to a correlation of 0.4 again. Okay. So this is an example of when we split, originally our correlation, actually let's go back and see what the correlation is. We didn't write it down. Our correlation is 0.577. So R equals 0.577. So my correlation was 0.577. When I split them into groups, because they do kind of still seem like they have the same relationship, and so having lots of points in the same relationship makes your correlation higher. When I split them into groups, my correlation did seem to drop. However, I would say that because these are so distinct, if I was doing this in a more advanced class, I probably still want to look at them separately. You might have noticed when I clicked color by gender, there was also another option to color by initials. Oh, never mind, I won't work on the applet. So another example, we can use the applet to analyze the FEV data set. So basically, FEV is a measure of how much, or it measures your lung capacity. Okay. So the explanatory variable would be your age. The response variable is your lung capacity, this FEV. And this is our original data set. Okay, I'd say looks like it's fairly strong. We have a positive relationship. But I can, when I pull it up, I click use data. I want to color by smoker. Okay. Oh, notice here, my age and FEV are actually switched. Okay, I wanted age to be my explanatory. So sometimes you can click here, but sometimes it has it here. So my response variable, I want to change to FEV. My explanatory variable, I want to change to age. Okay. So now I have age in the right spot. So coming back to our notes, okay, you can see that the red is all the way this entire pattern, okay, but the blue is only right here. Okay. So why are the blue dots, the smokers, only on the right side of the graph? Well, if you think about it, here's your age. So right about here, so I think it's telling you that there were no smokers under the age of 10, which is really sad to me that there are people smoking even at 10. Okay, but I would say the reason that there's no blue dots down there is that there were no smokers under the age of 10. Okay. Now, do they seem to have distinct patterns, or are they pretty mixed in together? I would say in this situation, they are pretty mixed in together. it does look like the blue dots might be slightly lower and the red dots might be slightly higher. Okay, but they're pretty mixed in. And so, like, do you think we need to subdivide our data into smoking and non-smoking groups before analyzing? I would say probably not. Okay, so one last note on observational studies versus randomized experiments. So before, these are our old definitions. Okay. Observational studies, we just observe and collect data. The researchers don't control anything. The experiment was that researchers assign subjects to groups. Okay, but the problem is when we have an explanatory variable that's quantitative, we can't just randomly assign people in categorical groups because there's not just a few groups. Okay, we're looking at numerical data. There could be lots of different possible X values. Okay, but what you can do is you can randomly assign people a value for the explanatory variable. So like if your explanatory variable is a dosage level for a new medicine, you could randomly assign different dosages to different people. So one person has 1 ounce, the next person has 2 ounces, the next person has 3 ounces, etc. Or if you want to test how the curing temperature of cement affects its strength, you could randomly assign different batches to different temperatures. So one batch is cured at 10 degrees, another at 20, another at 30, etc. So when you have a quantitative explanatory variable, an experiment means that the researcher assigns subjects values of the explanatory variable. So we don't put them into groups, but we do assign them a value. Like you have 100 Facebook friends, you have 200 Facebook friends, you have 300 Facebook friends. Okay. Random assignment would mean that the researchers randomly assign subjects to the different values. So you can randomly decide which one has 100 friends and which one has 200 friends. Okay. And so that's what makes an experiment is if the researchers control what level they are at. It's an observational study if we're just watching and collecting data.